Hello, this is a lecture on Chapter 5. We will be discussing equilibrium of a rigid body. Our objectives will be to develop the equations of equilibrium for a rigid body, which we've somewhat already started to discuss in Chapters 3 and 4. We're going to introduce the concept of a free body diagram for a rigid body, again, which will almost be review since we've already started to discuss free body diagrams. And we're going to be showing how to solve rigid body equilibrium problems using our equations of equilibrium. So we have a picture from the book, and it's a rigid body. And what we have are a bunch of forces and a bunch of moments acting externally on the object. If the object is not moving, if it's static, we could say that all of the sum of our forces are equal to 0, and all of our sum of our moments are equal to 0, meaning that they're pretty much canceling each other out so that it's not moving. We could break up our sum of our forces to some of our forces in the x direction and some of our forces in the y direction. And my nomenclatures, I say this is positive to up for the y and to the right for the x. And for my moment, I call positive going counterclockwise. Now, it would not be wrong when you're doing these to say this, but you've got to carry this out throughout all your equations and make sure that you write this on your equation if this is what you're going to be using so that I can follow your work. But most of the time, most books and many professors will use this counterclockwise is positive. We're going to be looking at a few of the supports that we'll be using a lot in this class. There are a bunch in your book. I believe they're on pages 210 to 211. So you actually from about 209 to 211, you're going to want to take a look at those. But the three that we're going to be using are a pin connection, a roller, and a fixed support. And so when we draw our free body diagram for, let's say, this roller, so I have my beam that's here. So a roller is not going to allow this beam to go up or down. So we have a reaction force in our y direction. So we'll call all these points A. That way we can just, so I would have A, Y here. For a pin connection, this is point A. Now the pin connection is not allowing it to move up or is it allowing to move it horizontally? So we would actually have a Y and a X. And for a fixed support, we've done it. My last example, I discussed a fixed support. We would have a Y because it's not allowing it to go up or down at point A. It is not allowing it to move horizontally at point A. And we also have to have a moment about point A in order to hold it. So if we had a bunch of forces acting on it, if this was some kind of bookshelf or something, these books would be holding pushing down on this, it would be causing a rotation about point A. So you have to have a moment about point A to hold this in equilibrium. Now, where would you see a roller? Well, you could see a roller on University Bridge where it's a beam bridge. You'll have a roller on one side so that it allows it to move horizontally so that way the concrete can move a little bit as it expands, as it gets smaller so that because of weather so that it doesn't crack. So those are important deals to look at. If you look at here, here's a rocker support for a bridge. Sometimes you'll have a big wheel so that it allows it to go back and forth. So you could have a rocker or a roller in this case. Here you have a pin connection, so it's not allowing it to go up or horizontally. This one is allowing it to move horizontally, but will not allow it to move vertically. Okay, let's go ahead and take a look at this. Let's say we have a simple beam here. If I have a simple beam, let's see if I can draw a straight line here. If I have a simple beam, gosh, that's a really ugly line. One more try. Alright, it's about as good as it's going to get. I'm going to draw my reaction forces at point A. So my reaction forces would be AY and AX since it is a pin connection. At point B, I would just have BY. And then I would have my forces labeled as well. And I would have my distances labeled. And let's just do this. That way it makes it easy. A, B, C, and D. And those would be my distances. So this is what I would be looking for your free body diagram. And being able to draw this will help you compute whatever we're looking at. They may give you reaction forces and you have to solve a force to keep it in equilibrium. Or you may have to solve for all the reaction forces, which is mostly the case, especially now that we're going to start getting into our trusses. We have to solve for our reaction forces in order to solve for all of our forces within our members, given some forces on a truss. So the three examples that I'm going to be showing next will be to solve reaction forces giving some type of forces on a beam. You could also have a moment somewhere in here. Or if we said this would be a couple, right? We could say that this force here and this force here, force 1, equal in magnitude, have a distance, you'd have a couple or a moment. Now why would we show it as a moment? Well, if we summed our forces in the y, F1s are going to cancel each other, so all we have to do is worry about the actual rotation that's happening at that point. We could also have a distributed load, whether it's rectangular or whether it's triangular distributed load on this beam where we would have to come in and find our point loads and their locations from the previous chapter in order to help solve our reaction forces. Alright, so I'm going to upload a few examples. Please let me know if you have questions. Thank you.